Hello, everybody. So we are going to start now the discussion on the methods that we use to calculate or formulate an equation that we can use to describe the and calculate the pressure losses in internal flows. But before we go through the equations and the details of these equations, there is a point that I want to make clear before we start, which is how do we formulate these equations. So we have two approaches. It's not only for this pressure drop, it's a general idea about any equation that we want to formulate for any system that we're interested in. So we have two approaches. The first approach is the approach that is based on theory, which means that we start the formulation of the equation by the basic equations or basic laws of physics, like the conservation of mass, conservation of energy, like force balance. And this is what we did in the previous chapters. And if you remember, when we reached the form of Bernoulli equation, or to prove that there is the pressure at a point under a fluid is going to be the same from all direction. These were all based on theory. We started with force balance or with and the equation for continuity equation, for instance, it started with the conservation of mass equation. So these are all equations that are based on theory. We put the basic theory, and then we define this equation that based on this theory that describes our system, based on some assumptions and based on the type of system that we are dealing with. And then we start with some mathematical manipulation for the equation. For instance, we can do some assumption. We can, from the assumptions, we can do integration. We can use the boundary conditions to find the final form of the equation. But at the end of the day, we will find or we'll end up with an equation that is that fully or describes the system based on the assumptions that we make in the beginning and the nature of the system that we are dealing with. And this is a very, very good approach because it doesn't require any experimental work. We just do this using mathematical derivations. We might need to do some experiments to confirm the equation, but at the end of the day, it's not part of the development of the equation. And also it gives a lot of understanding of the physics behind the equation. So we know where the equation starts from and we know how it ends, and that's how we get a good insight about the factors affecting the system from a theoretical point of view. However, there are some limitations to this approach. And this depends on the type of system that we're dealing with. And if the system is a simple system, then the equations that will describe the system are simple equations. And in this way, we can go through this approach in a simple way. But as the systems get more and more complicated, the equations that describes these systems become also more complicated, and this is expected. And as it gets more complicated, either it will be very, very hard to deal with from a mathematical point of view, so we cannot do the math to convert these equations into final form that we can use directly. We can just end up with a differential equation that we cannot deal with. But this is what we are going to see in the last chapter when we see Navier-Stokes equation. Or we cannot even reach this point. So we cannot find equations that can take all the parameters into account. So that's why this approach sometimes fails to work properly. So the other approach is that we depend on the experimental data instead of theory. By this approach, we will do a lot of experiments. We will gather a big amount of data, and we will use data fitting or any mathematical way like regression or something else in order to find an equation that properly describes the system that we are dealing with. This approach has an advantage of being valid for all cases. We are not limited to complex or simple systems. We will do the experiments anyway, so it's going to work. But of course, it requires a lot of experimental work and it requires a lot of time so that we can reach this point where we have enough data to fully describe the system. And of course, it requires some mathematical work and a lot of fitting and trying different equations until we reach a form of an equation that is properly defining the system. So anyway, so what we're going to do here is we are going to go for both approaches. So we are going to start with this method for a simple system, and then we are going to move to the other one, which is the more practical equation that we are going to use. So let's start with the derivation based on a theoretical or based on theory. And in this case, we have, as I just mentioned, we have to deal with a simple specific case. In this case, we are dealing with steady flow, laminar flow, incompressible flow, and a Newtonian fluid. I didn't put it here, but it's also for an incompressible flow and Newtonian fluid with constant properties. So the properties, by this we mean that there is no change in temperature or any other parameter that affects the properties. And it's in the fully developed region, so it's not valid for the entrance region, and it's for straight circular pipes, so and horizontal also. So it's horizontal, straight circular pipes. So if it's non-circular cross-section area, it's not going to work. So as you see, it's a very specific case. And to do this, we are, and as I said, we are interested in finding the pressure losses, which is the decrease in pressure as the fluid proceeds or moves forward in a pipe or tube. So the velocity is, as we see here, this is the velocity profile that we have seen many times before. The velocity, as it's a steady state and fully developed region, so the velocity profile is going to be the same everywhere. Okay, so the velocity is only function of the radius, not function of the axial length. But the pressure is going to be function of the axial dimensions and in the length of the pipe, because it's decreasing as the fluid moves forward. So that's why we need, as we do all the time, we'll take an element of the fluid and we'll do the balance on it. So the element has to have two differential dimensions: the differential length, because this is where the pressure is changing with, and the differential radius, because this is what the velocity is changing with. We take this as a circular pipe, so there is no change in the angular direction. So whether you rotate it at any angle, the profile is going to be the same for both the pressure and the length and the velocity. So that's why the shape that we picked here is this. This shape is not in the textbook. I drew it myself because I wanted to make it more easily to imagine. So this is a disc, a hollow disc that has a thickness dr and has a width dx, and it has a radius r. And this is what we are going to use as the differential element. And what we see here is the same as this, but this is a section, so we are cutting it in two halves. So what we see here is a rectangle that is a section that has width dx and length dr, up and down, of course, and above and below the center line. And the pipe has a radius uppercase r, and any radius would be the lowercase r. Okay. So this is the element that we're going to apply our equations on. So if you take a look at this element, we have forces acting on this element, and since this is steady state and fully developed flow, and there is uniform flow. So in this case, I mean, it's a fully developed flow. Then we have the net force will be 0. On each element, because it's constant velocity. Okay, so we will do force balance and put the summation of forces is 0. There is no acceleration, so the summation of force is 0. And now we want to take a look at the forces acting on this element. So remember that we have the flow is only in the axial direction. So the flow will cause forces either on this surface or in this surface. What is acting on this surface is perpendicular to it, and the same here. And what is acting on the two surfaces is parallel to them. So this is why it's shear force. So this is normal force, which is a pressure, and this is parallel force, which is going to be the shear stress. Okay, so If we want to calculate the forces, then each one of these pressures or stresses has to be multiplied by the area where it's acting on. So for the pressure, it's acting on this area here. Okay, so the area, this area is 2 pi r dr, okay, which is this area, and the shear force is acting on this area, which is 2 pi r dx. Okay, so this is what we'll see here. The pressures are multiplied by 2 pi r dr, and the pressure at x plus dx is also multiplied by 2 pi r dr, and the tau, which is the shear stress at radius r, is multiplied 2 pi r dx, and at r plus dr is multiplied by 2 pi r dx. Okay, so this is the force balance. Of course, what is in the positive x direction is positive, what is in negative x direction is negative. That's why we have this negative px plus dx and negative tau r plus dr. So we can divide this whole equation by 2 pi r, 2 pi dx dr. So if we divide this equation by 2 pi dx dr, it's going to be like this. We got the r out of the this fraction because the radius is not or the pressure doesn't depend on the radius. Okay, it's the same pressure at this whole small differential element. While for the tau depends on the radius, because at r it has a value and at r plus dr it has a value. So we grouped them here, r tau at r plus dr minus r tau at r divided by dr. This shape is dp by dx, and this is dr tau by dr. So this is the differential of the pressure with respect to x, and this is of r tau with respect to r. So this is the equation that we have here, and now we can apply the or find a formula for the tau. So we said that we have this as a Newtonian fluid, and for a Newtonian fluid, tau equals u times du by dy. And this is, we don't have y here, we have r. So we want to write this equation as du by dr instead of du by dy. So if we look here, we can see that y, the definition of y is the distance from the surface, from the solid surface. So this y is this distance here. Okay, so if we define y as this distance, is going to be r minus the uppercase r minus lowercase r. So this is why we define y this way. And now if we want to write this equation as tau multiplied by mu du by dy, instead of this to be du by dr, we can use the chain rule. So du by dy is du by dr times dr by dy. It's a very, very well-known rule in calculus. So if you differentiate this with respect to y, so if you get the dr by dy, so we get the derivative with respect to y. Dr by dy is going to be -1. This is constant, so the derivative is 0. So dr by dy is going to be negative. Dr by dy is 1. So dr by dy is -1. So it's negative du by dr. So we can write the tau as negative mu du by dr. And if we put it here, we can have this equation written this way, and we can get mu out of the integral and the minus out of the integral, or the differential, I'm sorry, and then put it the other way, or on the other direction. So this is what we have here. So this equation now is a partial differential. It should be partial. I think I did a mistake here. This should be partial, not d. So this is partial differential equation. This is the change of pressure with respect to x, and this is the change of the velocity with respect to r. So we have two independent variables, which is going to be very hard to be dealt with in a mathematical way. However, if we can prove that this is constant, it's going to be an ordinary differential equation, and we can keep it as it is, as a constant, and we don't change or we don't consider this in the integration. And to do this, we can do the same force balance, but instead of having this on the hollow disk, we can do this on a full disk of the fluid, taking the whole area, and the shear here is going to be the shear at the wall. So you have 2 pi r dx multiplied by shear at the wall, and the same on the other direction. And in this way, we have the shear in the same direction for both sides, because it's the whole area. So it's the shear has the same direction on the top and the bottom side from the symmetry. And we have pi r squared. This is of course the uppercase r because it's the whole area, and this is pi r squared p plus dp. And if we do the same thing, we can write the equation as dp by dx is -2, and of course this is the same dp by dx as before. It's negative tau w over r, which is constant. And we say it's constant because the shear at the wall is constant in or based on the assumptions that we make, that it's steady flow, that it's there is no change in the velocity with time, or the shear force with time, so it's going to be the same everywhere. So this is constant. It means that dp by dx is constant, which makes dealing with this equation now easy. So we are not going to include this as part of the differentiation. It's a constant. Put it as c if you want, and now we can do the integration. So it's going to be simple double integration. We have two constants, and from the boundary conditions we know that the velocity at the wall is 0, so at r equals r capital U is 0, and we know that the profile is symmetric around the center line, so it means that the derivative of the velocity with respect to r here is 0. So dur by dr is 0 at r equals 0. So if you apply these boundary conditions, we can reach the final form of the equation, and this is what we want to find at the end, that the velocity at any radius can be defined as negative r squared over 4 mu times dp by dx, which is constant, times 1 minus r squared over r squared. Of course, you might think that this is something wrong because the velocity is negative here, but this is not right because the change in pressure is negative because the pressure decreases. So the final pressure minus the initial pressure is always going to be negative. So this is negative by multiplied by negative, so it's going to be positive. So this is one thing. The other thing is that this is second order, which is equation, which is a parabolic profile of the velocity, which is what we see. Or we knew from the beginning that the velocity profile will be a parabolic profile. Now there is one more thing here that we can mention in this part, which is the average velocity. So if we want to get the average velocity, we can apply the same equation that we knew from before, the 1 over area times the integral of u times the area, the integration of u dA over the whole area. And by doing this, it's just math, it's simplifying the equation, doing the integrations, and applying the limits of integration from 0 to r, and at the end this is what we will get, that the average velocity is r squared over 8 mu times dp by dx. And if we want to get a relation between the average velocity and the velocity itself at any radius, we can combine these two equations. We can get u at any radius r is 2 times the average velocity multiplied by the bracket where it's 1 minus r squared over r squared. And if we put r equals 0, which is the center line, then the average or the maximum velocity is double the average velocity. Okay, so this is a good equation, a good output that we got from here, that we now know how to get the velocity profile. And by the way, this equation is called the velocity profile, which means that how the velocity varies with radius, which is a mathematical way of expressing this shape. Okay, so this is how we express this mathematically. So we know the velocity profile, we know how the velocity varies, or the average velocity can be calculated, but then there is a very valid question here, that we said that we do this derivation to get the pressure drop, but all what we calculated is the velocity profile and the average velocity. So how can we get the pressure drop? So this is what we're going to discuss the next video, inshallah. So I'll see you then.